Welcome to this discussion about solving trigonometric equations. And so this is kind of a lengthier discussion because there are several different techniques that we are going to talk about. But in this very first video, we are going to talk about really what is the gist of solving a trigonometric equation. We're going to look at it graphically, and then we're going to solve some simple trig equations for what's called a general solution. So let's take a look at this. So if we're looking at the graph here in the upper left-hand corner, you notice that there are really two graphs happening, right? The red graph is a partial graph of the function y equals the cosine of x. Okay, and then the blue graph is a partial graph of the function y is equal to the square root of 2 over 2. Now I say it's a partial graph because of course we know that both a cosine function and a constant function go on infinitely to the left and to the right. Consider if we are interested in where the cosine of x is equal to the square root of 2 over 2. That would be where the graphs intersect, okay? So we are really looking for the x values of the points of intersection there. The x values of the points of intersection are the solutions to the equation where we set those two things equal to each other. All right, so now let's think about this for a second. Can you identify where those points of intersection are and what are the x values? Let's work on this first quadrant first, okay? We've got one at pi over 4, and then we've got one at 7 pi over 4. Now if I go back to the second quadrant, I've got one at negative pi over 4 and negative 7 pi over 4. Okay. Does that mean that that's all of the solutions? Would there ever be any more? What if we extended the graph? Well, of course, if we extended the graph, we're going to see that those functions are going to intersect several more times. And we could actually generalize where those happen because they're going to happen every 2 pi units, because between these two solutions is 2 pi, and between these two solutions is also 2 pi. And actually, if we extend this graph, we can see that we've got a pair of solutions every 2 pi units, right? Do you see how that pattern repeats every 2 pi units? Okay, so how many solutions are there to that equation? That's where we're talking about all the solutions or the general solutions, and there's an infinite number of them. Let's think about the unit circle with the same equation. Cosine of x is equal to square root of 2 over 2. Well, how would you use the unit circle to find the values that satisfy this? Well, if we know the cosine of x on the unit circle are the x coordinates, all we're looking for are the angle measures that have an x coordinate that is the square root of 2 over 2. So, here's one at pi over 4. And then we are not going to see it again until what? 7 pi over 4. But are those the only values that would satisfy it? And of course the answer is no, because I could keep going around the unit circle, right? If I know I've got a solution here at pi over 4, well, what happens if I come around and add 2 pi to that? I'm still going to have an x coordinate of square root of 2 over 2. So I can add successive revolutions of the unit circle to find every possible solution to that equation. So in general, when we talk about a general solution to a trig equation, our sine and cosine general forms of equations are going to look like this. X will equal the solution or solutions. Sometimes we have 1, sometimes we have 2, plus 2 pi n. Now what's that 2 pi n? That's the period repeated any number of times because it doesn't matter how many times you repeat that period, we're still going to get a solution that works. Now tangent will be a little bit different because tangent will be in the form x is equal to the solution or the solutions plus pi n, and that is because the period of tangent is pi. Okay, and again, we can do it any number of times. So n can be any integer, any positive or negative integer, and that would be satisfactory. Okay, so let's give this a shot with solving trig equations. Okay, needed a little bit of that backstory in order to do this successfully. All right, so find the exact general solution to each trig equation. Okay, so when you're asked for a general solution, this is really saying find all possible solutions. Okay, so either one of those means the exact same thing. All right, so here are 4 examples, and if there's only one trig function involved, then there's really just 2 steps. The first step is to isolate the trig function, and the second step is then to isolate or solve for the variable. Now you notice that in these examples, the trig function is already isolated, so we don't have to really worry about this step in these examples. We will look at some examples in a moment where we've got to isolate the trig function. So let's look at this first example. The cosine of x is equal to the square root of 3 over 2. Now you can think about this graphically, but most students really think about this using the unit circle. And if you want to have a unit circle in front of you, that may be a good idea. Or many of you have used it enough that you have these things in mind. When I come up with my solutions, what I'm really thinking about once I've got that trig function isolated is all the angles on the unit circle that have this value, the square root of 3 over 2, as output. In this case, I'm looking for all the angles on the unit circle that have a cosine of the square root of 3 over 2, or an x-coordinate of the square root of 3 over 2. All right, so we can say that that happens at pi over 6 and 11 pi over 6. Now remember that with a general solution, we are going to add this plus 2 pi n as part of our answer because that's really saying that I can add 2 pi an infinite number of times, and the solutions that come out from that will satisfy this equation. So in this case, if I'm looking at this pi over 6, if I added 2 pi, I'd get 13 pi over 6. If I added 2 pi again, I'd get 25 pi over 6. If I subtracted 2 pi, I'd get negative 11 pi over 6. And if I subtracted 2 pi again, I'd get negative 23 pi over 6. But there's an infinite number of these solutions. So who wants to write them all out? No one. So we shorthand this by just saying plus 2 pi n instead of writing every single thing out. And we couldn't do that anyway because there's an infinite number of solutions. Okay, so let's look at the sine of x is equal to negative 1/2. So what are we thinking there? We are thinking what angles on the unit circle have a y-coordinate of negative 1/2. Okay, so grab that unit circle, take a look, but you should get 2 answers. You should get 7 pi over 6 and 11 pi over 6, and since we're using our general solutions, we are going to add that plus 2 pi n since this is a sine function. How about this next example? The tangent of x is the square root of 3 over 3. So what are we thinking about? We are thinking about what are the angles on the unit circle that have a ratio of y over x of rad 3 to 3. And this is where really knowing those tangent values comes in handy. This is going to happen at pi over 6 in the first quadrant and 7 pi over 6, okay? And when we write our general solution for a tangent, we add the expression plus pi n. Now notice that in this particular solution, pi over 6 and 7 pi over 6 are exactly pi units apart. So I don't actually need to write this second solution explicitly because it's really covered in this first one. Okay, it's not wrong if you do, it's just not necessary. So I'm just going to cross that out. Because if I add pi to this pi over 6, I'm going to get this one anyway. All right, and then the last one we've got is the cosine of x is equal to -1. So we're on the unit circle. Do I have a cosine of -1? Where is there an x coordinate of -1? And you should find that at pi. And of course, we would add that plus 2 pi n. Now notice this is one that only gets one solution out when I'm thinking about my unit circle. So why is that? Well, often when we are dealing with quadrantal angles, there is only one solution. Aside from those, you should always be looking for two solutions. When you've got a quadrantal angle as the solution, or you may have either one solution or two solutions. Otherwise, you're probably going to have two. So let's look at some examples where we have to actually isolate the trig function first. Okay, here we go. And these we're going to use the same strategy, but we will have to isolate the trig function before we go any further. And what do I mean by that? Well, if I'm looking at this equation, what is the trig function? The trig function is sine of x. So I want to isolate sine of x before I solve for the variable. So I would subtract a square root of 3, and then I would divide by 2, and I'd have the sine of x is equal to negative square root of 3 over 2. So now I'm thinking about the unit circle, and I'm thinking, well, what angles have a y coordinate of negative square root of 3 over 2? And I know those to be 4 pi over 3 and 5 pi over 3. So I would go ahead and add that plus 2 pi n on both of those. Okay, so let's look at this middle example. We want to isolate the trig functions, but there's two of them. Oh, I'm going to have to combine like terms here. Let's subtract 3 cosine of x to the left. So we've got 2 cosine of x is equal to the square root of 3. And now divide out that 2. And so I'd have cosine of x equals the square root of 3 over 2. And now let's isolate the variable, okay? So let's think about, on the unit circle, which angles have an x coordinate of the square root of 3 over 2. And we're thinking x coordinate because we are looking for cosine. All right, and so we can say that that will be pi over 6 and 11 pi over 6. So our solutions will be pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n. All right, last example here. We've got 7 tangent of x plus 8 is equal to 2 tangent of x minus 1. So let's add 2 tangent of x to both sides, and let's subtract the 8 on both sides. And we would end up with 9 times the tangent of x is equal to negative 9. Now when I divide through by 9 here, I get the tangent of x is equal to negative 1. And so now I'm thinking about, okay, on the unit circle, where do I have a tangent that's negative 1? And that should be at 3 pi over 4 and 7 pi over 4. And remember, we want to be careful with tangent, we're adding pi n. Oh, but aren't these just pi units apart? So I don't really need that second one either. Okay, so that wraps up this first video on some simple trig equations with a general solution. In our next video, we are going to talk about how do we solve trig equations that have arguments that imply multiple angles. And I will see you then.